All right, in this lesson we are going to talk about the E2 reaction, which is a new type of reaction related to the SN2 reaction, but it is different, unique, and fun. It's also a bit harder than the SN2 reaction. So we're going to start this lesson off with Introduction to Elimination Reactions. We'll oftentimes abbreviate reactions RXNs. And this is going to be the E2 reaction we're going to start with. And so let's take a look at an example of a bad SN2 reaction, because E2, it turns out, is in a constant competition with SN2. They're always fighting for each other, and may the best man win. So let's take a look at a bad SN2 reaction. And one of the worst SN2 reactions I can imagine is when the substrate sterics are extremely bulky. So let's take a carbon and let's actually put on 3 methyl groups. And we know that tertiary substrates, that is, when the alpha carbon has 3 beta carbons, that is a tertiary substrate and it's very bad for SN2. Now this top methyl group, I'm actually going to draw out the hydrogens on that methyl group. Okay. And so if you take a nucleophile and you attempt to do SN2, it doesn't work because SN2 fails on tertiary substrates. We've seen that before. And the reason is that it's very difficult for the nucleophile to get into the backside attack to kick off the leaving group. So I'll just draw a little arrow here to show there is no SN2 product. SN2 fails for tertiary substrate. No SN2. Tertiary substrate. But just because there's no SN2 reaction doesn't mean there's no reaction at all. In fact, it's the E2 reaction that predominates. And what happens is very similar to an acid-base reaction. The nucleophile, instead of going for the carbon, kicking out the leaving group directly, instead it's attracted to one of the beta hydrogens. It actually is going to kidnap one of those beta hydrogens on one of the beta carbons. There's a lot of beta hydrogens. I just picked one at random. We'll talk about how to predict which one. Sometimes there is some that are preferred over others. And then what that's going to do is it's going to take those electrons that were normally forming that carbon-hydrogen bond, and they are going to collapse to form a carbon-carbon double bond, also known as an alkene. And then that is going to kick out the leaving group. So the product of the reaction is actually an alkene. So E2 occurs, elimination occurs, and the product looks like this. The beta carbon now only has 2 hydrogens on it versus the original 3. The alpha carbon no longer has a leaving group, but it still has the 2 methyl groups on it. And if we look at the byproducts of the reaction, the nucleophile gets protonated, it gets an H, plus the leaving group leaves still. So this is the E2 reaction. In a substitution reaction, the product is replacing the leaving group with the nucleophile. In an E2 reaction, the product is an alkene. So we'll talk more about this, but let's look at an example problem that you might see on an exam. So example. I'll give a molecule. Let's say this guy right here. Okay. And maybe the first question I'll ask is, okay, this will be question 1. Perform a substrate sterics analysis. Okay, what that means is determine the degree of substitution and the beta branching. So I'll redraw the molecule here. And you'll notice that this is our alpha carbon, and this is our beta carbon. All right, so since we have 1 beta carbon, that means the degree of substitution is primary. And then looking at the beta carbon, how many carbons are attached other than alpha? 2. So the beta branching equals 2. Okay, that's all I mean by perform a substrate sterics analysis. We're done. The substitution is primary, and the beta branching is 2. Okay, that's an easy question. That's a softball question. Let me give you the harder question, which is question 2. Draw an E2 mechanism and product. Draw the product using potassium tert butoxide as base. Okay, again, I'll draw the substrate, and I'll draw the base, which is potassium tert butoxide, which looks like this. By the way, potassium tert butoxide is very popular for E2 reactions. The reason is that it's a very strong base, but it's also very bulky, so it's a poor nucleophile. So it's bad at doing SN2, because remember that a bulky nucleophile is bad at SN2, but it's still a very strong negative charge on an oxygen. So it's fine for E2, but bad for SN2. That kind of forces it into E2 territory. So you'll see that tert butoxide used a lot. And then the mechanism is going to involve one of the beta hydrogens. In this case, there's only one beta hydrogen. That's a hydrogen attached to the beta carbon. This is alpha, and this is beta. So it's going to attack a beta hydrogen. The electrons are going to collapse and form a double bond between alpha and beta. And then we're going to kick out the leaving group, bromine. The product is going to be this alkene. And notice that the alkene always forms between beta and alpha. The alkene always forms between beta and alpha. I'll say it one more time. Alkene always forms between beta and alpha. Okay, remember that. That's going to be key. So where I want to go next is, how do we predict whether E2 or SN2 will work? Is there a set of rules that we can use, we can apply, an algorithm, if you will, that'll allow us to determine which reaction is favored? And the answer is yes. Let's just take a look at a few examples to see how sensitive a reaction can be towards E2 or SN2. So E2 is almost always competing with SN2. You know, it's kind of like Burger King and McDonald's. When you're hungry and you need food in 5 minutes, are you going to go to Burger King or McDonald's? Well, it kind of depends which one's closer. Right? It's kind of the similar idea. For the purposes of this reaction, though, it's going to depend on a number of factors. The most important factors are substrate sterics, because substrate sterics really matter for SN2. You can really slow down an SN2 reaction if you have a sterically hindered substrate, but E2 doesn't really care about that. And also, base strength and bulkiness. If the base is really big, it favors E2. So let's take a look at some examples. If we take propyl bromide and treat it with potassium tert butoxide, the product is E2. So we get that alkene out, plus the protonated base, which happens to be terbutanol, plus the leaving group, which is KBr. And so this would be E2. Take a look at another example. Let's take this molecule here. If we treat it with NaOH, we are going to do an E2 reaction. And we'll get the alkene, as shown, plus the protonated base, which is H2O, plus the leaving group, which is NaOTS. And this is going to be E2. All right, let's take a look at another example. If we take this starting material, the exact same starting material, And instead of treating with NaOH, we treat it with NaSH. Suddenly SN2 becomes preferred. And the product is SN2. Remember that inversion occurs at the leaving group. So if you look at this, the only difference between example 2 and example 3 is the nucleophile. NaOH versus NaSH. Just replacing one atom, oxygen to sulfur, suddenly that flips our preferred product from E2 to SN2. That's a very subtle change. So I'll just say that. Wow. Subtle change. But it had a big impact. So how are we going to develop a way to predict E2 and SN2? Because that's going to be very important. I'm going to give you 2 starting materials, and you're not only going to have to tell me what product forms, but you're going to have to decide which reaction occurs. And the conditions for each reaction, SN2 and E2, are extremely similar. So we need a good way to 100% of the time predict which reaction will be preferred. How? Use a table. And we're going to draw a table on the next page that's going to help us decide. And the table is going to look something like this. It's going to be 2 columns. There's going to be an SN2 column and an E2 column. And we're going to perform a ranking in each column. In the SN2 column, we're going to perform a ranking based on substrate sterics. And in the E2 column, we're going to do a ranking on base strength. And based on the results in this table, we'll be able to predict which reaction predominates. And this is fun. I love this. I think this is super cool because you really get to analyze all the different factors in the reaction and decide and predict which reaction will be preferred. And this works. This is an amazing method. I love this method. So let me show you. First step in our method is to identify the leaving group. You must identify the leaving group. If you don't identify the leaving group, you're going to potentially be wasting a lot of time, because if there's no good leaving group, there's no reaction. It doesn't matter. SN2 and E2 both require one of our 5 good leaving groups. So if you don't have one of the 5 good leaving groups, save your time. There's no reaction. Number 2, second step is identify the nucleophile. Okay, now all you need to do is identify the nucleophile. We're not going to be able to say no reaction based on the nucleophile, but it's going to be important to fill out our table knowing our nucleophile. Okay, now this is what our table is going to look like. As I mentioned, there's an SN2 column and there is an E2 column, and I'm going to leave a lot of room here because I'm going to explain what each column looks like. Okay, so I'm going to draw a line here. I'm going to draw a line here. I'm going to draw a line here. That may be too long of a line, but we'll trim it if necessary. Okay, now I'm also along the left-hand side going to write good, fair, poor, and not applicable. Okay. The SN2 column will be based on the substrate sterics. So if you have a primary substrate, your SN2 column will be ranked as good. And remember, the substrate is referring to whatever the leaving group is attached to. A secondary substrate is said to be fair. And a tertiary substrate will be said to be poor. For not applicable in SN2 column, its SN2 is going to be Na if you have a poor or bulky nucleophile. And for the poor nucleophiles, there's a list on Canvas that lists the poor nucleophiles, which, by the way, are alcohols, water, and carboxylic acids. And then for the bulky nucleophile, the only bulky nucleophile you need to worry about is the tert butoxide. That's the only bulky nucleophile you need to worry about. Now for the E2 column, that's going to be based on the base strength. So if we have a strong base, the E2 column is said to be good. And if you have a moderate base, it's said to be fair. And if you have a weak base, it's said to be poor. And what about Na? No beta hydrogen on substrate. Right? E2 requires a beta hydrogen. So if there's no beta hydrogen, E2 is going to be NA'd right away if there's no beta hydrogen. That means you need at least one hydrogen attached to a beta carbon. Now, you may be wondering, well, how do you define strong, moderate, and weak base? That seems kind of arbitrary. It turns out we're going to have a very specific way to define these things. A strong base will be defined as the following. A substance whose pKa of the conjugate acid, so we have to look at our pKa table, is greater than or equal to 16. So this is not the pKa of our nucleophile, it's the pKa of the conjugate acid of our nucleophile, meaning you have to add a proton to it and then look at the pKa table. We'll do examples of that. For the moderate base, that's going to be a pKa of conjugate acid of 0 to 16. And a weak base will be pKa of conjugate acid less than or equal to 0. And that's our table. Now, we look at a reaction, we choose good, fair, poor, Na for the SN2 column and for the E2 column, and then choose the first best option. In other words, you choose the best option, but if there's a tie, you choose the first best option, which means SN2 is going to win. So SN2 wins ties. Okay, so this all sounds like a bunch of gobbledygook, I know. Let's do some real examples, and you'll see how awesome this method really is. Okay, so let's do an example here, and we're going to predict which reaction will predominate. So I'm going to take this alkyl halide, it's a propyl bromide, and we're going to treat it with NaOH. And then the question is going to be, is it SN2 or E2? Okay, let's do our table method. Oh, but wait, before we do our table method, step 1, I almost forgot. Don't forget, what's step 1? Identify the leaving group. Do we have a good leaving group? Yes, we have bromine, which is one of our good leaving groups, so we can move forward. But if we didn't have a good leaving group, don't bother wasting your time with all the other steps. Step 2, identify the nucleophile. What's our nucleophile? It's NaOH. We'll keep that in mind. And then now we can do the table. So our table looks like this, SN2, E2. Okay, SN2 column first. First things first, do we have a poor or bulky nucleophile? No, we do not. NaOH is not a poor nucleophile because it's not water, an alcohol, or a carboxylic acid. Be careful, NaOH is not an alcohol. A lot of students think whenever they see OH, they think it's an alcohol, but NaOH is sodium hydroxide. It's not an alcohol. An alcohol is oxygen attached to carbon. There's no carbon attached to this oxygen, so it is not an alcohol. It's sodium hydroxide, which is quite a strong base. It's also not bulky. It's not tert-butoxide. There's no tert-butyl group attached, so it's not a bulky nucleophile. So we're just going to assign good, fair, or poor. And is our substrate primary, secondary, or tertiary? We look at the alpha carbon. We see that there's one beta carbon, so that means it's primary. So that means SN2 is good. Okay, now it's time for E2. For E2, we need to look at the conjugate acid of our base, or our nucleophile. So NaOH. What's the conjugate acid of NaOH? It's H2O, right? If NaOH, if OH minus gains a proton, it becomes H2O. The conjugate acid has a pKa equal to 16. Use your pKa table and you'll see that H2O has a pKa of 16. pKa of 16 or greater is considered a strong base. So good. We have a tie. SN2 and E2 are both good. So who wins? SN2 wins ties. So the answer is that SN2 will predominate. So now that we know that SN2 is the winner, we can predict the product. So when we add NaOH to this bromide, it's going to replace the bromine with the nucleophile, which is OH minus. So our product will be the substitution product shown. Awesome. Okay, we got a lot more examples to do, so let's keep going. Take a look at example 2. Okay, let's figure out which reaction predominates, and let's figure out what the product is. Okay, in this situation, the leaving group is bromine, which is one of our 5 good leaving groups, and our nucleophile is NaOH. We'll keep that in mind. Now we can fill out our table, SN2, E2, and you'll start to get pretty fast at this. SN2, it's a secondary substrate. If you look at the alpha carbon, there are 2 beta carbons, so it's secondary. So that is fair. And then for the E2 column, our nucleophile is NaOH. The conjugate acid of NaOH is H2O, which is, we just saw on the previous page, the pK is 16. For H2O, which is the conjugate acid of our nucleophile, so that's going to be good. All right, who wins? Well, in this case, SN2 is fair and E2 is good, so E2 wins. We choose the first best option. E2 is the best option. So we can draw the product. Sorry, I lost my... We can draw the product. And remember, to draw the product of an E2 reaction, you just draw a double bond between alpha and beta. We have alpha, but we have 2 betas. We have beta to the left and beta to the right. So that means we end up actually making 2 products. We make this product here, which is the double bond between alpha and beta to the left. And we also make this alkene, which is alpha and beta to the right. Of course, we lose our leaving group. All right. So that's the E2 reaction. Now, we'll actually turn out that one of these products is favored over the other. It's a major product. We'll talk about that next time. Now let's take a look at example 3. Okay, here's a nice one. We have a leaving group, which is bromine, which is one of our 5 good leaving groups. Our nucleophile will be NaOH. Okay, let's predict the product here. So SN2 column, E2 column. For the SN2 column, we look at the substrate sterics. It's primary. There's only 1 beta carbon in this molecule, so this is primary, so this is good. And what about the E2? Well, you might be tempted to look at the conjugate acid, 16, good, but look at the beta carbon here. Are there any hydrogens attached directly to beta? No. There's just carbons attached to beta, so there's no beta hydrogen. So that means the E2 column is actually Na, not applicable. Okay, so the winner, good is better than not applicable by a long shot, so SN2 wins. So our product will be as follows. We'll just replace our bromine with OH. Sweet. All right, let's do another one. I just love doing these examples. Okay, let's try butyl bromide plus KOTBU gives what? Okay, well, we have bromine, one of our good leaving groups. We have a nucleophile is KOTBU. Ah, that's a bulky nucleophile. So what does that mean? Well, when we do our SN2 and E2 column, SN2 is going to be not applicable because bulky. All right. And then E2, well, we need to look at the conjugate acid of KOTBU. So KOTBU has a conjugate acid, when you add an H plus, of HOTBU, hot boo, and that is an alcohol. All right, that has the structure that looks like this. And alcohol, if you look at your pKa table, has a pKa of 16 also, just like water. So E2 has a pKa of the conjugate acid equal to 16, which is good. So E2 wins. So our product will be the E2 product. So just erase our little question mark here. And we make a double bond between alpha and beta. Oops. There we go, 4 carbons. A double bond between alpha and beta. E2 is the winning reaction. All right, let's take a look at example 5. All right, first order of business, check for a good leaving group. Uh-oh. Not a good leaving group. Don't fall for my trick. OH is not a good leaving group, so that means no SN2 or E2. There's no reaction. Need a good leaving group for SN2 or E2. All right, let's do another one. NaOAC. Okay, what is this product going to be? All right, do we have a good leaving group? Yes, we have iodine as well, it's actually our best leaving group. And what's our nucleophile? Our nucleophile is NaOAC. What is the structure of NaOAC? If you recall in your abbreviations list, OAC is the acetate group. So this is actually equal to Na plus O minus. It's a deprotonated carboxylic acid. So the conjugate acid equals HOAC, which equals acetic acid. Acetic acid has a pKa equal to 5. So that's going to be important for our table. Okay, so SN2, E2. Our SN2 column is going to be secondary, right? Our substrate is secondary, so fair. And our E2, our pKa of our conjugate acid is carboxylic acid, which is 5. 5 is between 0 and 16, so that's also fair. So we have fair and fair. It's a tie. SN2 always wins ties. So now we can predict our answer will be an SN2 reaction. So if we have our substrate and we treat it with NaOAC, we're going to replace our leaving group with OAC, and don't forget to flip the stereochemistry. And so that's our product there. Looks good. Okay, one more example, I think. We do one more example? Yeah, let's do one more example. Okay, and our example is going to be this one here. Okay, let's try this one. Do we have a good leaving group? Yes, bromine is one of our 5 good leaving groups, so that's a fantastic leaving group. And our nucleophile is NaNH2. What's our conjugate acid? If we add an H+, we get NH3. That's an amine. The conjugate acid of an amine is 38 from our pKa table. Okay, so now we can do our table. SN2, E2. For the SN2, this is a tertiary substrate, so poor. For the E2 column, the pKa of the conjugate acid is 38, which is very high, which means NaNH2 is a very strong base. So this is going to be good, greater than 16. So E2 is our winner. So we'll just draw a double bond between alpha and beta as our product. So Br, NaNH2. And so then our product will be looking like this, right? Because remember, this is alpha and this is beta. So I'm just going to, there's actually 3 betas, but I'll just pick one of the betas at random and put a double bond in between alpha and beta, and then the other 2 carbons stay the same. That's our E2 product. All right, so that's a lot of examples of predicting between SN2 and E2, and you'll have some bonus problems to try and figure these guys out on your own. It's a lot of fun. Okay, just a couple of details I want to talk about And then in the next lesson, we're going to talk about how to better draw the E2 products, because I've been just drawing these double bonds pretty quickly. You know, like I just drew this, and that may be confusing to you. So that's going to be the focus of next class, is just more practice actually drawing the products of E2. But this lesson was mostly focusing on, can you just predict that E2 is going to occur? Yes, we can. Okay, there's just a few more details I want to share with you, because our discussion of the E2 reaction would not be complete without these details. Okay. And these details are as follows: hybridization, alkene stability, and finally, this is also, by the way, sometimes called Zaitsev's rule. And then the last thing I need to mention is conformations. Okay, first thing we need to talk about is hybridization. Okay, the conversation we need to have about hybridization is two things. First of all, the leaving group must be on an sp3 hybridized carbon, just like SN2. Leaving must be on sp3 carbon. And this is true for SN2 and E2. But there's another thing that's true just for E2, and that is that the beta hydrogen must also be on an sp3 carbon. And that is only important for E2. Let's take a look at an example of what I mean by this. So if I took this alkene here, and we want to do an E2 reaction, let's draw in all the hydrogens. So there's a hydrogen, the beta hydrogens. There's a beta hydrogen there, and then there's 3 beta hydrogens here. And it turns out that only the beta hydrogens attached to the sp3 hybridized carbon are okay. So that means these guys over here, only these are okay. This hydrogen right here is not attached to an sp3 hybridized carbon. It's attached to an sp2 hybridized carbon, so it cannot be eliminated in an E2 reaction. So only the right hydrogens can be eliminated, which means the alkene is only going to be formed to the right. So after an E2 reaction, we only form the elimination towards the hydrogens that are sp3 hybrid attached. Okay. Next thing I want to talk about is alkene stability. Let's take a look at an example to demonstrate what I mean by this. Okay. How many possible E2 products could form from this starting material? Let me draw in the hydrogens. Okay. How many possible products can we form? Well, if we eliminate from the right side, the methyl groups, the methyl hydrogens on the right, we would end up with this alkene. It's eliminating towards the beta carbon on the right. If we eliminate towards the beta carbon on the left, we would get this alkene. But we would also get, potentially, the cis alkene. There's a stereochemistry possibility also for that. So there's actually 3 alkenes possible from this one substrate, and it turns out that the most stable one is this one here. Okay, and so what's the rule to help us pick the most stable alkene? So if you have multiple beta CH bonds, go to the product that is A, most substituted. That means go to the alkene that has more carbons attached and fewer hydrogens attached. Take a look at this alkene. How many hydrogens are a part of that alkene? 2. There's 2 hydrogens on that alkene. How many hydrogens are part of this alkene? 3. So the fewer hydrogens you have attached to the alkene, the more stable it is, and we call that more substituted. So you want to go to the alkene that is more substituted, and we call that Zaitsev's rule. This guy did a lot of E2 reactions, and he found that you generally, most of the time, get the more substituted alkene. That is the alkene with the fewest number of hydrogens on it. You also want to go to the alkene that is trans, or E stereochemistry. And that makes sense. We've talked before about how the cis alkenes are higher in energy because there's more eclipsing interactions, versus in the trans alkene, you can have the methyl groups are further away from each other. So remember that, just to recap, cis is when you have the bigger groups on the same side of the alkene, and trans is when you have the bigger groups on opposite sides, and trans is better. And then you may sometimes hear me use words to describe the substitution of alkenes. So this alkene is considered monosubstituted because there's 1 carbon attached. This alkene is disubstituted. This alkene is also disubstituted. You could have a trisubstituted alkene with 3 carbons attached to it. And you could even have a tetrasubstituted alkene with 4 groups attached. So it turns out that tetrasubstituted alkenes are more stable than monosubstituted alkenes. It turns out that CH bonds in alkenes are pretty high in energy, so it's better to have more carbons attached to an alkene. Okay. All right, last thing we need to talk about, and it's the hardest thing about E2 reactions, and that is conformations. And we'll talk more about this next time. Conformations matter. Specifically, the beta hydrogen must be anti-periplanar. Oof, what does that mean? It means 180 degrees from each other in the same plane. Let me show you what you want it to look like. You want it so that the H and the Br, or whatever the leaving group is, the beta hydrogen and the leaving group are not wedged or dashed, but they're flat in the page, and they're also zigzagged. That's anti-periplanar. So you want them both to be flat, no wedges or dashes on the hydrogen, the beta hydrogen, or the leaving group, and you want it to be zigzag. That is perfect conformation for a E2 reaction. Product would just be the simplest alkene. So let me show you an example of what that would not be. So let's take a look at a complicated molecule here. Okay, look at this molecule here. Check out our leaving group, our bromine, and our beta hydrogen. I've highlighted them both in yellow. They are not anti-periplanar. They're both on a wedge, but anti-periplanar, they both need to be flat and they need to be zigzagged. In other words, the leaving group needs to be where the phenyl is, and the hydrogen needs to be where the methyl is, and then we would have an anti-periplanar relationship. So let's actually do a rotation, the merry-go-round method. If you remember, we did that a little bit on an earlier problem set, where you have to rotate the bonds inside of the molecule so that the H and the Br are antiperiplanar, and then do the elimination reaction. This is going to have an important consequence on the stereochemistry. So let's try that. I'm going to redraw that molecule over here. And this is hard. This is confusing and this is hard. Okay, we need an antiperiplanar relationship. So what we're going to do is we're going to rotate the left carbon to put the H where the methyl is. If we put the H where the methyl is going to move to where the ethyl is, and the ethyl is going to move to where the H was. Okay, so let's do that. So we're going to have the H where the methyl was. The methyl will go to where the ethyl was, so that's going to be a dash. And then the ethyl will go to where the H was. So we haven't changed this molecule, we've just rotated that carbon like a propeller or like a merry-go-round to put the H in the right position. And now let's do the same thing with the bromine. The bromine needs to get to where the phenyl is. So move the bromine to the phenyl will move to the H, and the H will move to the bromine. So that'll put the Br where the phenyl was. The phenyl goes to where the H is, and the H goes to where the bromine was. It'll look like this. And now look what we have. We've enabled that key antiperiplanar relationship. Now we do the elimination reaction. So that's going to give us an alkene. And then on the right carbon, we have an H and a pH. And then on the left carbon, we have a methyl and an ethyl. But now all you need to do, now that we're in the reactive conformation, make sure that the wedges are with the wedges and the dashes are with the dashes. So in this case, the ethyl and the H are both wedged in the reactive conformation. So that means they're going to be on the same side of the alkene. So put the ethyl on the top. The phenyl is a dash, so it's going to be on the same side as the methyl. So I'll put the methyl on the bottom with the phenyl. And so this is going to be the E alkene. Not this. This would be a diastereomer, not Z. So by rotating into the reactive conformation, that allows us to determine which product forms, E or Z. It's decided by the reactive conformation because we need to put the H and the ethyl together since they're both wedges, and that's exactly what we did. It doesn't matter if they're both on the top or both on the bottom, but just remember this, wedge with wedge, dash with dash. That's going to lead us to this product here. Okay, we're going to do a lot more examples of that next time, but I just wanted to get your mind ready for what's going to have to potentially be done with some of these E2 reactions. You may have to rotate them in order to find the right stereochemistry of the product. Okay, see you guys soon.